And today we're diving into a book that truly changed the game.
We really are. We're looking at where we came from, how the universe began, all of it.
We are, of course, talking about Stephen Hawking's revolutionary work, A Brief History of Time. It's this incredible exploration of cosmology and quantum mechanics that just completely changed the public's relationship with science.
It really did. I mean, the success of this book was just, it was unheard of.
Totally. We're talking about a book that spent 237 weeks on the London Sunday Times bestseller list.
Which is just staggering. It really proved that people were hungry for these big answers, even if they involve some, complex physics.
And Hawking pulled off something amazing. He famously joked that he sold more copies than Madonna's book on sex. So our goal today is to unpack this whole journey, piece by piece. We're tracing human thought from, Aristotle's spheres all the way up to M-theory.
Okay, so before we jump into that history, Hawking sets the stage. He defines what makes a good scientific theory. Why is that so important to start with?
Well, it's really the foundation of everything that follows. For Hawking, a good theory has to do two things, and they're non-negotiable. First, it has to be elegant.
Elegant.
Yeah, it has to accurately describe a huge range of observations, but based on a model that's as simple as possible, with very few arbitrary bits tacked on.
So simplicity is key.
Exactly. And the second thing is it has to be predictive. It needs to make definite predictions about things we haven't observed yet.
Because if it can't, it's just describing the past. It's not a real tool for understanding.
Precisely. That search for elegance and predictability is what drives this entire story.
Okay, with that standard in mind, let's start at the beginning. Chapter 1. Our picture of the universe.
We have to start with Aristotle, back in 340 BC. This is long before we had satellites or anything like that, but he had really compelling evidence that the Earth wasn't flat. He argued it was a sphere.
It's amazing what they could figure out with just observation and logic. So what were his big proofs?
Well, the first was the shadow of the Earth during a lunar eclipse. He noticed it was always round.
Right, a flat disk would cast a long, straight shadow sometimes.
Exactly. The only way it's always a circle is if the object casting the shadow is a sphere. The second proof was about travel. As people journeyed south, the North Star appeared lower in the sky.
Which only makes sense if you're on a curved surface.
Right. And he even tried to estimate the Earth's circumference. He was way off, about double the real value. But the fact that he even tried is incredible.
So he got the shape of the Earth right, but his picture of the cosmos was still very Earth-centric.
Oh, completely. His model had a stationary Earth right at the center. And the sun, the moon, the planets, they all moved around us in perfect circles.
This view gets formalized later by Ptolemy, right? In the 2nd century AD.
It does. Ptolemy builds this incredibly detailed geocentric model with 8 nested spheres. But it had a big obvious problem right away.
The planets don't move in perfect circles. They do that weird retrograde motion thing.
They do. To account for that, Ptolemy had to add these smaller circles, epicycles, that the planets traced as they moved along their main orbits. It got very, very complicated.
And even he knew it wasn't quite right. I remember reading that his own model predicted the moon should sometimes look twice as big as it does at other times.
Which it obviously doesn't. But the model stuck around for over 1,400 years. And it wasn't just because of scientific inertia, it offered a kind of philosophical comfort.
How so?
Well, with the fixed stars on the outermost sphere, it left a very clear space outside our universe for heaven and hell. It fit neatly into the Christian worldview of the time. It gave the universe a clear, ordered structure.
And that kind of certainty is hard to give up. The first crack in that wall comes in 1514 with Copernicus.
Right, and he was so worried about being branded a heretic that he circulated his heliocentric model anonymously at first.
His model was so much simpler, wasn't it? The sun's at the center, Earth is just another planet.
And that immediately explains retrograde motion. It's just an optical illusion. It's what happens when a faster-moving Earth overtakes a slower-moving outer planet.
But it took a real revolution, a real observational proof to make it stick. And that came with Galileo.
In 1609, he turns the new telescope to the sky, and what he sees is just undeniable.
He saw Jupiter's moons.
He saw Jupiter's moons, orbiting Jupiter.
Yeah.
Not everything was orbiting the Earth. That was the nail in the coffin for the geocentric model.
But even Copernicus's model wasn't perfect because he stuck with circular orbits. It took Johannes Kepler to figure out they were actually ellipses.
Exactly. But they still didn't have a why. Why do the planets move in ellipses? What's the driving force?
And that brings us to Isaac Newton in 1687 and his Principia Mathematica.
Probably the most important single work in the history of physical science, because Newton provided the universal explanation.
The law of universal gravitation, the same force that makes an apple fall, keeps the moon in its orbit.
Exactly. Everybody attracts every other body with a force that depends on their mass and the distance between them. This explained Kepler's ellipses not as some random rule, but as the natural outcome of a universal force.
But this created a new paradox for Newton, a really big one. If gravity is always attractive, why hasn't the universe collapsed?
It's a great question. Newton realized a finite number of stars would just fall in on themselves. So to keep his static internal universe, he proposed it must be infinite.
The idea being that the pull would be equal in all directions, so nothing would collapse.
Right. But it's a very unstable balance. And as people pointed out later, dealing with infinity is tricky. The slightest nudge and the whole thing comes crashing down anyway.
And this leads to another huge problem for the infinite static model, Olber's paradox.
Yes, popularized by Heinrich Olbers in 1823. The question is simple. Why is the night sky dark?
If the universe is infinite, with infinite stars that have been shining forever,
Then no matter where you look, your line of sight should eventually end on the surface of a star. The whole sky should be as bright as the sun.
and you can't even argue that dust blocks the light.
No, because eventually the dust would heat up and start glowing just as brightly itself.
So the darkness of the night sky tells us something fundamental. Either the universe isn't infinitely old, or it isn't static.
Or both. And that's where Edwin Hubble comes in the 1920s. His observations completely changed everything. He found that distant galaxies are all moving away from us.
And not just moving away, but the farther away they are, the faster they're going.
That was the death blow for the static universe. If you run the clock backward, everything comes together at a single point in the past.
A singularity. The Big Bang?
Around 10 to 20 billion years ago. And that brought the question of a beginning, of creation, into the realm of science. To understand that, we had to pare down our old ideas of reality itself.
Which brings us to chapter 2, space and time.
So, we have to start by replacing Aristotle's ideas about motion. He thought the natural state was rest, and you needed a force to keep something moving.
Galileo was the one who really tested that, right? The story about dropping things from the Tower of Pisa might not be true, but he did do experiments rolling balls down ramps.
Right, and he proved that all bodies accelerate at the same rate, ignoring air resistance. Newton then took that and formalized it. Force doesn't cause motion, it causes a change in motion, acceleration.
And that's a huge shift. It means there's no absolute state of rest, no absolute space.
Exactly. Think about bouncing a ball on a moving train. To you, it goes straight up and down. To someone on the platform, it's tracing these long arcs.
And both perspectives are equally valid.
Correct. The laws of physics work the same for both of you. There's no preferred frame of reference.
Okay, so if space isn't absolute, then time is next on the chopping block.
Right. It started in 1676, when Ole Romer figured out light travels at a finite speed by watching Jupiter's moons.
But the big moment was James Clerk Maxwell in 1865. He unified electricity and magnetism, and his equations predicted that light waves had to travel at a very specific fixed speed, c.
Which was weird. Physicists at the time assumed that speed must be relative to some invisible medium filling all of space, which they called the ether.
And then the Michelson-Morley experiment in 1887 tried to measure our speed through this ether.
And found nothing. The speed of light was the same no matter which way the Earth was moving. The ether wasn't necessary.
Enter Albert Einstein in 1905 and special relativity.
His big insight was to take both of those facts seriously. The laws of science are the same for everyone, and the speed of light is the same for everyone, no matter how fast they're moving.
And for that to be true, something has to give.
And that something was absolute time. If we have to agree on the speed of light, but we disagree on the distance it travels, then we must disagree on how long it took. Time is relative.
From that, you get all the famous consequences. EMC22.
Mass and energy are two sides of the same coin. And as you approach the speed of light, your mass increases. So it would take infinite energy to get there. Only massless things like light can travel at sea.
And because you can't separate an event from its position in space and its moment in time, they get woven together into one four-dimensional fabric, space-time.
Right. We even measure huge distances in units of time, like light years. They're fundamentally linked.
This unified view gives us the idea of light cones to map out causality.
It's a great way to visualize it. Imagine an event happens right now. The light from it spreads out, forming a cone into the future. That's the future light cone. Only events inside that cone can be affected by what just happened.
Because nothing can travel faster than light to carry the information.
Exactly. And there's the past light cone, too, containing all the events that could have affected this one. Everything else is in what we call the elsewhere. It's causally disconnected.
For example, the sun could vanish right now and we wouldn't know for 8 minutes. Anything happening on Earth in the next 8 minutes is in the elsewhere of that event.
Right. But special relativity only worked for uniform motion. It didn't play nicely with gravity. Newtonian gravity was instantaneous, which violates the light speed limit.
So Einstein had to go bigger. General relativity in 1915.
And this was his true masterpiece. Gravity isn't a force. It's the result of mass and energy curving the fabric of space-time itself.
The classic bowling ball on a trampoline analogy.
It's the best one we have. The bowling ball creates a dip. A marble rolling past doesn't get pulled toward it. It follows the straightest possible path, a geodesic on the curved surface.
So the Earth orbits the sun because it's just following a straight line through the curved space-time created by the sun's mass.
Precisely. And this theory made predictions that were immediately testable.
Like the weird wobble in Mercury's orbit.
Which Newtonian physics couldn't explain, but GR nailed it.
Yeah.
And famously, the bending of starlight around the sun, which was confirmed during a solar eclipse in 1919.
General relativity also predicts that time itself is warped. Time runs slower in stronger gravitational fields.
And this isn't just a weird theory, we use it every day. Your GPS wouldn't work if the satellites didn't constantly adjust for the fact that their clocks are running slightly faster up there, farther from Earth's gravity than our clocks down here.
It's the twins paradox. The twin who travels in a fast spaceship or even just lives on a mountain ages a tiny bit faster than the twin at sea level. Time is personal.
Exactly. And now, Chapter 3. The expanding universe applies these mind-bending ideas to the entire cosmos.
So after relativity, we really had to rethink our place in the universe. Hubble's work in 1924 showed that all those spiral nebulae were actually entire other galaxies way outside our own Milky Way.
Yeah, our galaxy is this huge thing, 100,000 light years across, but it's just one of about 100 billion others. And we're just an average star out in one of the spiral arms.
And to figure out how these galaxies are moving, astronomers use the Doppler effect.
Right. Just like a siren's pitch changes as it moves past you, the color of light from a galaxy changes.
If it's moving toward us, the light is compressed, shifted to the blue end of the spectrum.
Blue shifted. And if it's moving away, the light is stretched, shifted to the red end. Red shifted.
And Hubble's bombshell discovery in 1929 was that almost every galaxy is redshifted.
And not just that. The farther away a galaxy is, the greater its redshift. The faster it's moving away from us. The universe is expanding.
This was such a shocking idea that even Einstein had resisted it.
Oh, he hated it. He was so attached to the idea of a perfect, static, eternal universe that when his own GR equations suggested it should be dynamic, he added a fudge factor.
The cosmological constant.
Right. It was basically this built-in anti-gravity force to keep everything perfectly balanced and still. He later said it was his biggest blunder.
But there was a physicist who trusted the original equations.
Alexander Friedmann, a Russian mathematician. In 1922, even before Hubble's discovery, he solved Einstein's equations without the cosmological constant and predicted that the universe must be expanding.
He just assumed the universe was, on average, the same everywhere and in every direction.
And those simple assumptions led him to the right answer. The universe can't be static.
Okay, so the theory predicted expansion and Hubble observed it. But the real smoking gun for the Big Bang came later, by accident.
Yes, in 1965, Arno Penzias and Robert Wilson at Bell Labs. They were working with this super-sensitive microwave antenna, and they kept picking up this faint, persistent background hiss.
A noise coming from every direction in the sky, day and night.
They tried everything to get rid of it. They even, famously, cleaned out pigeon droppings from the antenna horn, thinking that might be it.
But the noise was still there.
Meanwhile, just down the road at Princeton, a team led by Robert Dicke was building an experiment to look for exactly that signal.
Because theorists had predicted that the hot, dense, early universe should have left behind a faint afterglow.
Exactly. An afterglow that would have been stretched by the expansion of the universe over billions of years, until today it would be visible as faint microwave radiation.
And Penzias and Wilson had stumbled right onto it, the cosmic microwave background.
The literal heat from the creation of the universe. It was stunning confirmation of the hot, Big Bang model.
So with the Big Bang model confirmed, the Friedman equations give us a few possible futures for the universe, don't they?
They do, and it all depends on how much matter and energy is in it. It depends on its average density.
So what are the options?
Option 1. If the density is too low, gravity isn't strong enough to stop the expansion. The universe expands forever, getting colder and emptier.
The big freeze.
Right. Option 2. If the density is high enough, above a certain critical value, gravity will eventually win. The expansion will slow down, stop, and reverse.
The big crunch.
And option 3. If the density is exactly at that critical value, the universe expands forever. But the rate of expansion slows down, approaching zero over an infinite amount of time. It's perfectly balanced.
But no matter which future is correct, they all point back to the same past.
A singularity. A moment of infinite density and temperature, where our laws of physics, including general relativity, just break.
And that singularity was something a lot of physicists tried to avoid. There was the steady state theory.
Right, proposed by Bondi, Gold, and Hoyle. Their idea was that matter was just continuously being created out of nothing, filling in the gaps as the universe expanded. So it could be eternal and unchanging.
But the discovery of the CMB really put an end to that idea.
It did. And the final nail in the coffin came from Roger Penrose and Hawking himself in 1970. Their singularity theorems proved that, within general relativity, a singularity was unavoidable.
So classical physics hits a wall. To understand the beginning, you have to go smaller.
You have to go quantum. Which brings us to Chapter 4, the uncertainty principle.
This is where we throw out the old idea of a deterministic clockwork universe.
Completely. For centuries, the dream was that if you knew the position and velocity of every particle, you could predict the future perfectly. Quantum mechanics says that's fundamentally impossible.
It starts with Max Planck in 1900, who realized that energy isn't continuous. It comes in discrete packets, quanta.
Right. And that led to this bizarre new reality of wave-particle duality. Light, which we thought of as a wave, sometimes acts like a particle, and particles, like electrons, sometimes act like a wave.
They're not in one specific place. They're sort of smeared out in a wave of probability.
And that's the core of Heisenberg's uncertainty principle. You cannot know both the exact position and the exact momentum of a particle at the same time. The more you know about one, the less you know about the other.
And this isn't because our measuring tools are bad. It's a fundamental property of the universe.
Exactly. The classic example is the two-slit experiment. You fire electrons at a barrier with two slits in it.
And if they were just tiny baseballs, you'd expect two bands on the screen behind it.
But that's not what you get. You get an interference pattern, a series of many bands, which is the signature of a wave.
Even if you fire the electrons one at a time.
Even one at a time. It's as if each single electron goes through both slits at once and interferes with itself. It's mind-bending.
But this weirdness is what saves the atom. Classically, an electron orbiting a nucleus should radiate away energy and spiral into the center.
But in quantum mechanics, the electron is a wave. And only certain orbits, where a whole number of wavelengths fit perfectly around the nucleus, are stable. That's why atoms don't collapse.
So quantum mechanics explains the very small, and general relativity explains the very large. But they don't agree.
They are fundamentally incompatible. GR is a classical theory. It's smooth and deterministic. QM is probabilistic and lumpy. And the singularity theorems show us there are places, the Big Bang, the center of black holes, where gravity is so strong that you need a quantum theory of gravity to describe it.
And that's a central problem of modern physics. To move forward, we need to know what everything is made of. So, Chapter 5, Elementary Particles and the Forces of Nature.
We've come a long way from the four elements of Aristotle. We discovered atoms, then found they were made of electrons, protons, and neutrons.
And then we smashed protons and neutrons and found they were made of even smaller things, quarks.
Right. An idea from Murray Gell-Mann. Protons are 2 up quarks and 1 down quark. Neutrons are 2 downs and 1 up. There are 6 types or flavors of quarks, and they have a property called color.
And all these particles have another property called spin. Why is spin so important?
Spin determines how a particle behaves in a group. All the particles that make up matter quarks, electrons, have a spin of 1/2.
And they obey Pauli's exclusion principle.
Which is one of the most important rules in the universe. It says that no 2 identical matter particles can be in the same place with the same properties at the same time.
They need their personal space.
They do. And thank goodness, because without it, all the atoms in your body would collapse into a dense, featureless soup. The exclusion principle is what gives matter its structure and solidity.
But the particles that carry forces are different.
Right, they have integer spins, 0, 1, or 2. They don't obey the exclusion principle. You can pile as many of them as you want into the same space, which is what allows them to create strong forces.
Before we get to the forces, there's another key idea: antimatter.
From Paul Dirac in 1928. His equations combining quantum mechanics and relativity predicted that every particle must have an antiparticle twin with the same mass but opposite charge.
And the anti-electron, the positron, was discovered just a few years later.
The key thing about antimatter is that when a particle meets its antiparticle, they annihilate each other in a burst of pure energy.
Okay, so these matter particles interact via 4 fundamental forces,
Which are carried by those force-carrying particles. First, the weakest of all is gravity.
carried by the still hypothetical graviton. It's weak, but it acts over long distances, and it's always attractive, so it adds up.
Then there's the electromagnetic force, carried by the photon. It's much stronger, but it can be attractive or repulsive, so on large scales, positive and negative charges tend to cancel each other out. It's what governs all of chemistry.
Then you have the 2 nuclear forces, which only act over tiny distances. The weak nuclear force.
Which is responsible for things like radioactive decay.
And finally, the strongest of them all, the strong nuclear force.
Carried by gluons. This is what binds quarks together inside protons and neutrons, and what holds the atomic nucleus together against the electromagnetic repulsion of all those positive protons.
And the strong force has these 2 weird properties: confinement and asymptotic freedom.
Confinement means you can never ever find a quark all by itself. They're always trapped in groups. And asymptotic freedom is the strange idea that when quarks are very, very close together, the strong force between them gets incredibly weak.
So the big goal in physics is to unify these forces, to show they're all just different aspects of one master force.
And the first big success was the electroweak unification.
Right, the Weinberg-Salam theory. It showed that at very high energies, like in the early universe, the electromagnetic and weak forces are actually the same thing.
It's a phenomenon called spontaneous symmetry breaking. At high energy, the forces are unified and symmetric. As the universe cools, that symmetry breaks, and they crystallize out into the different forces we see today.
And the next step is grand unified theories, or GUTs, trying to lump the strong force in with the electroweak force.
Exactly. These theories predict that at an even higher energy, all 3 of those forces become one. They also predict that protons should eventually decay, though we haven't seen it happen yet.
But this chapter has a huge implication for our own existence. Why is there any matter at all?
Right. The Big Bang should have created equal amounts of matter and antimatter, and they all should have annihilated each other, leaving just a universe full of light.
But there's a slight asymmetry, a flaw in the laws of physics.
A tiny one. The weak force, it turns out, isn't perfectly symmetric in time. This slight imperfection meant that for every billion antiquarks, there were 1,000,001 quarks.
And after all the annihilation, that 1 in a billion leftover is everything.
Every star, every galaxy, you and me, we are the leftovers from that slight imbalance in the laws of nature.
That is incredible. From the building blocks of matter, we now go to the most extreme objects in the universe. Chapter 6. Black holes.
The basic idea has been around for centuries, but really took general relativity to make sense of it. The term black hole itself is pretty recent, from John Wheeler in 1969.
And their formation is all about the life and death of stars. A star is this constant battle between fusion pushing out and gravity pulling in.
And when the fuel for fusion runs out, gravity wins. The collapse begins. And what happens next depends entirely on the star's mass.
This is where the Chandrasekhar limit comes in.
Yes. Subrahmanyan Chandrasekhar calculated that if a cold, dead star has more than about 1.5 times the mass of our sun, the force that holds up normal matter, the exclusion principle between electrons, will fail.
So stars below that limit end up as white dwarfs. What about stars above it?
They can collapse further, crushing the electrons and protons together to form a neutron star, an entire star's mass packed into a sphere maybe 10 miles across, held up only by the exclusion principle between neutrons.
But there's limit for that too. If the core is more than about 3 solar masses, nothing can stop the collapse.
Nothing we know of. It collapses all the way down to a point of infinite density, a singularity.
And surrounding that singularity is the point of no return, the event horizon.
That's the boundary.
Yeah.
It's the point where space-time is so warped that light itself can't escape. And since nothing can go faster than light, nothing that crosses the event horizon can ever get back out.
So let's talk at the poor astronaut falling in. What does someone watching from far away see?
They see something very strange. As the astronaut approaches the horizon, their clock appears to slow down. Their image seems to get redder and dimmer, and they seem to freeze, suspended at the edge for eternity, but never actually crossing.
But for the astronaut, it's a very different story.
For them, time flows normally. They cross the horizon in a finite amount of time without noticing anything special at that exact moment.
Although they would have some other problems.
Oh, yeah. For a normal-sized black hole, the tidal forces, the difference in gravity between their head and their feet, would stretch them into spaghetti long before they got to the horizon. In a supermassive black hole, though, they could cross intact, only to be crushed at the singularity a few hours later.
So Penrose and Hawking proposed the cosmic censorship hypothesis, the idea that the singularity is always safely hidden behind an event horizon.
Right. You can't have a naked singularity out in the universe, because it would be a point where predictability breaks down completely.
And once a black hole forms and settles down, it becomes incredibly simple. The no-hair theorem.
That's right. All the complex information about the star that formed it gets lost. The final black hole is defined by only 3 numbers: its mass, its spin, and its electric charge. That's it. It has no hair.
So how do we actually find these things if they're black?
We look for their gravitational effects on things around them. The best evidence comes from binary systems, like Cygnus X1.
You have a visible star that's clearly orbiting something invisible.
And by tracking the star's orbit, you can calculate the mass of the invisible companion. In the case of Cygnus X1, it's about 6 times the mass of the Sun. Way too heavy to be a white dwarf or a neutron star.
So it has to be a black hole.
It's the only thing that fits. And Hawking actually made that famous bet with Kip Thorne about it.
He bet that it wasn't a black hole, sort of as an insurance policy for his own research.
Exactly. If black holes didn't exist, a lot of his work would be wrong, but at least he'd win the bet. He eventually conceded and paid up.
A 1-year subscription to Penthouse magazine.
That's the story. Now there's one other type of black hole, primordial black holes. Tiny ones that might have formed in the dense early universe. And paradoxically, those tiny ones might be the key to Hawking's biggest discovery.
Which brings us to Chapter 7. Black holes ain't so black.
It started in 1970, when Hawking realized something about the area of an event horizon. He proved that the total area of all event horizons can never, ever decrease.
If 2 black holes merge, the new one has an area that's bigger than the sum of the original 2.
Right. And that sounded suspiciously like another law of physics.
The second law of thermodynamics. Entropy disorder always increases.
Exactly. A physicist named Jacob Bekenstein suggested that maybe the area of the event horizon is a measure of the black hole's entropy.
But that leads to a huge paradox. If a black hole has entropy, it must have a temperature. And if it has a temperature, it has to radiate heat.
But nothing can escape a black hole. It was a massive contradiction.
So how did Hawking solve it?
He brought in quantum mechanics. In 1973, he showed that black holes do, in fact, radiate. It's now called Hawking radiation.
So how does it work? How does anything get out?
It's a quantum effect happening right at the edge of the event horizon. You have to remember that empty space isn't really empty. It's filled with virtual particles, pairs of particles, and antiparticles that pop into existence for a fraction of a second and then annihilate each other.
Okay.
Right at the event horizon, a pair can be created where one falls in and the other escapes. The one that falls in has to have negative energy to balance the books.
So negative energy falls into the black hole.
Right, and its positive energy partner escapes out into space. From a distance, it looks like the black hole just emitted a particle.
And what does that negative energy do to the black hole?
According to EMC 202, it reduces its mass. The black hole slowly loses mass. It evaporates.
And as it gets smaller, it gets hotter and radiates faster.
Exactly. It ends in a final, tremendous burst of energy and disappears.
So those tiny primordial black holes we talked about would be incredibly hot and should be radiating away like crazy right now.
They should be. The fact that we don't see a huge background of gamma rays from them tells us that the early universe must have been extremely smooth and uniform.
So the big takeaway here is that gravitational collapse isn't a one-way street after all. Information isn't lost forever.
And it suggests that quantum mechanics might be the key to resolving the singularity itself, which leads us to the biggest questions of all in Chapter 8, the origin and fate of the universe.
So the standard hot Big Bang model works really well. It explains the expansion, the microwave background.
And it perfectly predicts the amount of helium in the universe. The model says that in the first few minutes, the universe was hot enough for nuclear fusion, turning about 25% of the hydrogen into helium. And that's exactly what we observe.
Later on, gravity pulls that matter together to form galaxies and stars, and those stars cook up the heavier elements we're made of.
But for all its success, the classical Big Bang model has 4 huge unanswered questions. Problems that suggest it's not the whole story.
Okay, what are they?
First, a simple one. Why was the early universe so hot? The model assumes it, but doesn't explain it.
The second is the horizon problem. The microwave background is the same temperature everywhere, to incredible precision. But regions on opposite sides of the sky are too far apart to have ever been in contact. How did they coordinate their temperatures?
Right. Third is the flatness problem. The expansion rate of the universe is fine-tuned to an absurd degree. If it had been slightly different a second after the Big Bang, the universe would have either recollapsed immediately or flown apart too fast for galaxies to form. Why the perfect tuning?
And number 4, where did the initial little lumps and bumps come from? You need some slight density variations to act as seeds for galaxies to grow.
Exactly. The classical model just hits a wall at the singularity and says, these were the initial conditions. It's not a real explanation.
So the first big idea to tackle some of these was inflationary theory.
Proposed by Alan Guth. The idea is that for a tiny fraction of a second, the very early universe underwent a period of hyper-accelerated expansion. It blew up by a factor of like $10 or more.
And that solves the horizon and flatness problems.
It does. Any 2 points that are far apart now were incredibly close together before inflation, so they had time to sink their temperatures. And the rapid expansion automatically flattens out any curvature in space and drives the density to exactly the critical value.
But it still needs a starting point. And that's where Hawking's most radical idea comes in, the no-boundary proposal.
This is deep in the weeds of quantum gravity. The key is to use a mathematical trick where you treat time as an imaginary number. In that framework, space and time become equivalent.
And what does that let you do?
It lets you describe a universe that is finite in extent, but has no boundary, no edge, no beginning or end.
Like the surface of the Earth. It has a finite area, but there's no edge you can fall off of.
That's the perfect analogy. In this picture, the universe doesn't start at a singularity. It starts smoothly from a single point, like the North Pole on a globe. It expands to a maximum size, the equator, and then could contract back to a South Pole.
So if there's no boundary, there's no beginning in the traditional sense.
Which means there's no need for a creator to set the initial conditions. The universe is a completely self-contained system, governed only by the laws of physics. It would just be.
And this idea even explains the seeds for galaxies.
It does. It predicts that the universe must have started with the smallest possible non-uniformity allowed by the uncertainty principle, tiny quantum jitters. Inflation then stretched those jitters to cosmic scales, and they became the seeds for all the structure we see today.
And this was confirmed.
The Kobe satellite in 1992 found those tiny temperature variations in the microwave background, and they matched the predictions of inflation and the no-boundary proposal perfectly.
The implication is profound. If this is right, the laws of physics alone determine the state of the universe. There's no room for arbitrary choice.
Right, and that self-contained nature leads us to Chapter 9, the arrow of time.
The paradox here is that the fundamental laws of physics don't really care about the direction of time. They're time-symmetric. But our world clearly has a direction.
Cups break, they don't unbreak. That's the second law of thermodynamics. Entropy, or disorder, always increases. This is what gives time its arrow.
Hawking identifies 3 arrows of time: the thermodynamic arrow we just mentioned, the psychological arrow, the direction in which we remember things, and the cosmological arrow, the direction of the universe's expansion.
And the psychological arrow is directly linked to the thermodynamic one. The act of forming a memory in your brain requires energy and increases the total disorder of the universe.
Yeah.
We remember the past, not the future, because our brains operate in the direction of increasing entropy.
So why do all 3 arrows point the same way? Why does disorder increase as the universe expands?
It goes back to the no-boundary proposal. It says the universe must have started in a very specific, highly ordered, low-entropy state. And since there are vastly more ways for a system to be disordered than ordered, it naturally evolves toward greater disorder.
So the initial condition sets the thermodynamic arrow, but what if the universe starts to contract again? Does the arrow reverse?
Hawking first thought it might, but later corrected himself. He realized that disorder would continue to increase even in a contracting phase.
So why do we find ourselves in the expanding phase where the arrows are aligned?
The weak anthropic principle. Intelligent life requires a strong thermodynamic arrow. We need to consume ordered energy, like food, to survive. A contracting universe would likely be a very high-entropy, disordered place, unsuitable for life as we know it. So we could only evolve in the expanding phase.
Fascinating. So the whole journey of this book pushes us toward one final goal. Chapter 11, the unification of physics.
This is the ultimate quest, and it's all about solving that fundamental conflict between general relativity and quantum mechanics.
Let's just quickly recap the problem. Why does combining them lead to nonsense?
It's those virtual particles again. When you try to calculate the energy of all the virtual particles in empty space, you get infinity. Infinite energy means infinite mass, which means space-time should be curled up into an infinitely small ball, which it clearly isn't.
So the theories break down. This is what led physicists to string theory.
Instead of point-like particles, string theory says the fundamental entities are tiny, vibrating one-dimensional strings. What we see as an electron is just a string vibrating in one pattern. A photon is a string vibrating in another.
And the beauty is that one of the vibrational modes of the string corresponds perfectly to the graviton, the particle that carries gravity. So it naturally unites them.
It does. And it comes with a price. To be mathematically consistent, string theory requires the universe to have more dimensions than the four we see.
10 or even 26 dimensions.
Right. The idea is that the extra dimensions are curled up so tightly that we can't detect them. And again, the anthropic principle is sometimes invoked to explain why only 3 space dimensions got big enough for us to live in.
And now even string theory is seen as just one piece of a bigger puzzle.
Yes. The discovery of various dualities and connections between different versions of string theory has led to the idea of a more fundamental underlying theory, which is often called M theory.
So is there an end to this? Will we ever find the ultimate theory?
We think there might be a limit. The Planck energy. At energies above this, particles would be so dense they would collapse into their own black holes. This suggests there might be a final theory, a complete description of reality.
And if we found it, Hawking argued it would be the ultimate triumph of human reason.
It's a powerful thought. The idea is that once we have it, it could eventually be simplified to the point where everyone can understand the basic principles.
And that would allow all of us, not just scientists, to take part in the discussion of why we and the universe exist.
For then, as he so famously wrote, we would know the mind of God.
So our deep dive has taken us from Aristotle's perfect spheres through the death of absolute space and time to the quantum fuzziness of the Big Bang itself.
And we end with this radical proposal. A universe that is completely self-contained with no beginning and no end, governed by a single unified set of laws.
In that view, the question isn't who started it all. The question is, what are the rules that made it all inevitable? The universe just is.
We want to leave you with that thought. Consider the power of that search for knowledge. What stands out to you about this journey, and how close do you think we are to truly understanding the ultimate laws that govern everything? Keep asking those questions.